Today, we are diving into classic system design interview question, how to design a URL shortening services like Tinyurl or Bitly. The core goal is simple. A user give us a long URL, and we give them a short, user-friendly link that redirects back to the original. Let's establish our functional requirement first. Shortening. Given a long URL, our service generates a unique short alias. Redirection. When someone clicks that short link, they are redirected to the original long URL with minimal latency. Custom expiration. By default, links last for a year, but users can specify longer period. And unique mapping to maintain ownership and varying expiration date. If two users shorten the same long URL, they should each get a unique short link. Now, for the non-functional requirements, we need high availability, scalability, and most importantly, ultra-low latency for redirects. Let's look at the scale. We are estimating 1 billion new URLs per month. If we have read-to-write ratio of 100 to 1, that means 1 read and 1 write. That means we are handling 300 reads per second. This is bring us to a crucial design question. Why we use base 62 instead of base 10? If we only used digits from 0 to 9, base 10, for an 8 character string, we will have only 10 of the power of 8. That's mean 100 millions combinations. At 1 billion writes a month, we will run out of ID in 3 days. By using the base 62, which is 0 to 9, A to Z, and capitalize A to Z, we will get 62 to the power of 8 combinations. That is roughly 3.5 trillion unique strings. At our current rate, we won't run out of ID for over 100 of years. This ensures our system is the future-proof. Where do we store this data? Each entry needs the short key, the long URL, a user ID, and an expiration date. On average, we are looking about from 100 to 1000 bytes per entry. Over time, this adds up to 2 terabytes of data. Here we have a comparison between the relational database, SQL, and NoSQL. While SQL is great for relational data, Tinyurl is basically a giant key-value store. We don't need the complex join or ACID transaction for the mapping itself. Basically, the NoSQL is the winner here. It's allow for eventual consistency. If its replica take 2 seconds to receive an URL mapping, that's an acceptable trade-off for the massive risk scalability NoSQL provides. However, as we will see in a moment, we might still want a SQL database for one specific part of the system. How do we actually generate the key? If we hash the URL using MD5 or SHA, we get a long string that we have to truncate, which leads to collision. Checking the database every time to see if a key exists is slow and expensive. The better solution here is a key generator service. We pre-populate dedicated SQL database with unique and used base62 strings. Why SQL here? Because ACID properties. When our servers need a key, they fetch it from the key generation service. Because we use SQL atomic transaction and locking to ensure that once a key is read, it's marked as used immediately. This prevents two different users from getting the same short link at the exact same time. To make it even faster, the key generator service can load a buffer of a key into memory cache. If the key generator service node crashes, we lose that buffered key, but since we have 3.5 million of them, losing a few thousands is a tiny price to pay for the speed boost. When a user clicks a link, how does the redirect happens? The server sent 301 moved permanently or 302 found HTTP status code. 301, it's better for performance because the browser will cache the mapping. Next time the user clicks, their browser doesn't even ask our server. It goes straight to the long URL. At 302, it's better if you want to track every single click for analytic, as it forces the request throughout the servers every time. 300 reads per second. We absolutely need the cache layer. We should use the LRU, the least recently used eviction policy. Why? Because some links go viral for a day and then die. LRU ensure that only the currently popular links stay in high-speed memory. Finally, we have to handle the leftovers. We have a cleanup service that runs asynchronously. It scans our database for the expired links, delete them to save space, and return those keys to the key-generated service as unused, so they can be recycled. For global scale, we use load balancers to distribute across multiple web servers. Database partitional, we can partition our data using consistent hashing based on the short link key or the user ID. This ensures that as we grow, we can just add more database nodes without a massive headache. To wrap up, Tinyurl is a classic example for picking the right tool for the specific job. We use the base 62 to ensure we have trillions of unique IDs, NoSQL to handle massive read-heavy scaling, and a dedicated key generator service with SQL ACID properties to prevent link collisions, adding an LRU cache for lightning fast redirects and async cleanup service to recycle old key, and then you have a system built for global scale. The most important takeaway: system is all about trade-off. Whether you choose 301 for speed or 302 for analytic depend entirely on your business goals. Thanks for watching.